to the afternoon session. Our first speaker is Franco Flandoli of the Scuola Normale Superiore from Pisa, who will be speaking about remarks on the 2D inverse cascade.
Thank you. Thank you so much for the honor to be here to give this talk, which is a little bit risky because the subject is unclear, and certainly my contribution is poor. Let me try to explain first what is the inverse cascade in few words. In 2D fluids, in two-dimensional fluids, layers of fluids, if the energy, some energy like small vortices are injected, let's say a small scale in the sense they are small vortices, then it is observed that larger structure builds, and if this mechanism of injection is maintained, so there is a stationary regime, in this stationary regime we observe this inverse cascade, which has a special scaling law. The scaling law, so precise, can be conjectured on the basis of next slide, classically, but is also experimentally verified. And so it is similar to the three-dimensional direct cascade law, with the difference that in experiments here it is very precise, and in 3D it is not. And so maybe from the mathematical viewpoint this could be a test field where one could try to prove something, construct some theory. This is the energy spectrum. I don't need to define it for the rest of the talk. Just remember that there is this special formula, and for us to understand something I will reach at the end of the slides, if u is a typical velocity at scale r, the analog of this is this law. So the velocity increments scale r, scale like r to 1/3, and this epsilon is the energy flux, the flux which is in the energy injected per unit of time and space into the fluid. And the explanation that is extremely simple but correct in some sense is by dimensional analysis. By the way, it's the same explanation in 3D, in 3 dimensions, except that the intuition behind is the opposite. It is based on two assumptions, namely that this energy spectrum, case wave number, energy spectrum, the modulus of the norm, Euclidean norm of the wave number in 2D, the energy spectrum depends on k and on the energy flux and nothing else, and the dependence is of power law, or scaling law. Made this since k has dimension L-1, the energy is a little bit tricky. Please accept that Ek has this dimension, is easy exercise. The injection has a certain dimension because it is related to the time derivative of the energy. This is also a little bit tricky conceptually, but and the time enters here in a very interesting way. Then equating the two at the level of dimension, there is a relation. And then the time is here, so alpha is immediately equal to 2/3, and L, let me show in the next slide, alpha is equal to 2/3, and then you compute beta, which is 5/3. And both numerical experiment and some physical experiment confirm quite well that there is a range of these wave numbers in which the slope minus 5/3 is relatively accurate, but not the full range, of course. And the pictures of this kind of turbulence are complex, as usual in turbulence, and seems to show many scales, even if we should blow up some region to see better. So the question is to have some mathematical theory which explains this inverse cascade and this spectrum, because I mean, the dimensional analysis showed before is very fast, gives essentially the correct result, but the same dimensional analysis in 3D gives a result which is not completely correct, so in itself cannot be a complete explanation. It's just a very fast explanation, and it is based on assumptions that are plausible. This fact that everything depends only on K and the flux of energy, but not so directly observable. And in addition, there are no equation of motion, and the mechanism of why this cascade happens and why the spectrum appears is not explained. So it's very, very simple, but one can hope to do better. And what about the equations? This is, so to speak, the accepted equation by the community, namely I forgot to write a divergence of u equals 0. U is the velocity, incompressible, fluid, omega is the vorticity. The equation is already written for the vorticity. This is two-dimension. In 3 dimension, the equation for the vorticity is different, but here is just a transport of vorticity by the velocity, the time derivative, dissipation. The viscosity coefficient is usually extremely small, so this dissipation plays a secondary role, but probably not a 0 role. And important is this mechanism of friction. So alpha is a friction coefficient because layers of fluid are in contact with with other object, and so they experiment friction. So the friction is very important to dissipate, and usually there is a mechanism of creation of energy at some scale, which in this case is a small scale, I assume, to generate energy at small scale. And I will simplify in the sequel, neglecting the viscosity. The viscosity could play a role, certainly plays a role in the so-called anomalous viscous dissipation of entropy. I will come later about that. So from that viewpoint is fundamental. From the energetic viewpoint, I don't think so. So I neglect it for the time being from the energetic viewpoint. And other things that is good to know from this slide is that this quantity called entropy, the integral of omega square, is mathematically, if you do a trivial computation, is conserved for these models, but exactly for some reason there is an anomalous dissipation of this for sure. You will see. Energy on the opposite is conserved. Energy is the integral of u square. This is conserved exactly because there are a priori bounds for a quantity which is of higher order in terms of regularity. So the a priori bound on this give that the energy is conserved. And but this is almost surely dissipated by in an anomalous way, even if we forget about the Laplacian. And the problem concerning turbulence could be maybe stated in terms of finding invariant measures. So here there is an input, a dissipation by friction, a mechanism, and to find an invariant measure which incorporates in some way inverse cascade and the energy spectrum that I wrote at the beginning. And there is obviously a theoretical path to do that, namely to study the same equation with the Laplacian, the Navier-Stokes, with, for instance, here white noise. And why I mention this? Because with the Laplacian it's possible to prove uniqueness of invariant measure under many conditions on the kind of noise, and here I listed some of the people that contributed. And so uniqueness of the invariant measure with the Laplacian is known, and so the right object should be the limit when the viscosity goes to 0, but they are a little bit abstract object, let's say. I mean, certainly the family of measures depending on the viscosity is tight. This is not a problem, but so limit points exist, but possibly are non-unique, and in any case we don't have quantitative information on this object from that viewpoint. There are beautiful papers of Cooks in Shirikayan trying to get some information, but not so strong yet. Here I start the series of slides with another simplification, then I go back to the question of the previous slide. Simplification in which forget about force and friction, just to understand the invariant measure of this. So I write a series of slides just to in case you have never seen, but probably you know, to see that there are a lot of invariant measures explicitly known. So I will write a lot of known invariant measures just for comparison with the true problem, let's say. These invariant measures, explicit, are either concentrated on point vortex configurations, or they are related to white noise and modifications of white noise. Let us see what I mean. The general idea is to define in a Gibbs way using these two quantities that I already mentioned are invariant, formal invariant, the entropy and the energy. The energy can be rewritten in terms of omega using the Green function on the space domain where we work. So one can write everything in terms of omega and write this Gaussian measure, because it's quadratic, this Gaussian measure on some space of omega. But what is the meaning of this? First, let us see in the case of point vortices. So I call point vortices the case when the vorticity is concentrated as delta Dirac in certain points, so with intensities. These intensities have the physical meaning of circulation. So the gamma I, for the whole lecture, there will be this gamma I that are the intensities of point vortices, and xi are the positions. The positions have to satisfy this law, this equation, where k is the curl of the Green function. It's called the Biot-Savart kernel, and the Green function, I forgot to, probably is written below, is logarithmic in the distance between x and y, and the Biot-Savart has this kind of singularity, like Coulomb, let's say, this singularity at the origin, but this is the orthogonal, so it's a rotating vector field. And so this is the dynamic of point vortices, and this is a vorticity field, distributional, because it's sum of delta Dirac associated to this dynamic. And one has to introduce the interaction energy. The self energy is infinite. The kinetic energy of a point vortex, unfortunately, is infinite because this kernel is not integrable in R2, let's say, or also in bounded domain. I mean, the singularity in the origin of that kernel is not integrable. The interaction energy between the different I and j, different vortices, is well defined as soon as the vortices occupy different positions, and this sum with the intensities and the log of the distance, here is written log of the distance, this quantity is called interaction energy, and this is an invariant. It's an invariant for the dynamic written in the previous slide, this dynamic. For this dynamic, this interaction energy is invariant. And so based on that, and also the Lebesgue measure is invariant, because one can discover that the previous system has an Hamiltonian structure. And so at the end of the story, if you take this measure built by Lebesgue and this invariant quantity, this is an invariant measure for the point vortex dynamic. Well known. I'm talking about well-known things. This invariant measure, the point vortex dynamic, is finite dimensional. It lives in the if we call D the domain where there are the vortices, it is in d to the power n. But we can map this invariant measure to an invariant measure for Euler, because the point vortex dynamic is a very weak solution of Euler equation. One can formulate Euler equation using a special trick called Choquet symmetrization in a way that this distributional object that I wrote here, the sum of delta Dirac, is rigorously a weak solution of Euler equation written in this special weak form. And
Is it possible for the point vortices to coalesce?
yes, but not almost surely in the initial condition. So all my stuff will be randomized from the viewpoint of initial condition because of the Gibbs measure, etc. And so they don't meet almost surely in the initial condition. Otherwise, you can build a special configuration that coalesce. Yes, that's true. Or one can avoid with Massimiliano and Enrico Priola. We prove the theorem that if we put a suitable noise, then coalescence is avoided by the noise for every initial condition. So it's possible to avoid coalescence in different ways. And this Gibbs measure on the point vortex motion, of course, can be shifted to an invariant measure for Euler. So for the PDE Euler, interpreted in a very weak form, if we consider the map from the position of the vortices to this distributional vorticity field, the Gibbs measure here goes into a measure here, which is supported on finite signed measures, on the space of finite signed measures, which is included in this Sobolev space. This Sobolev space will appear again later, so this is why I mentioned this Sobolev space. And the image measure is invariant for Euler. Let me call it mu beta n. So mu beta n will be the image measure on vorticity fields for finite number of points and inverse temperature beta. Onsager claimed that beta negative, which is unusual, is interesting in the case of fluid dynamic, and this is very important. What is the effect of beta negative? Beta negative means that minus beta is positive, and so the highest probability configurations are those with high energy, high interaction energy. The interaction energy in terms that is written here assume that the intensities of the circulation, the intensities of these vortices are the same sign. So take vortices with the same sign, or here, and they tend to be close each other because high energy, when this is a positive coefficient, if the 2 points are very close each other, the logarithm is negative, with this minus is positive, and gives a big contribution to the interaction energy. And so the negative beta corresponds to high energy configurations, correspond to favor high energy configuration, and so the typical configuration of this Gibbs measure, when beta is negative, are aggregated sets of vortices, because aggregate sets of vortices of the same sign tend to be aggregated, the negative together, the positive together. This was understood by Onsager. There is a long literature on it. I quote the works of this group of people because are rigorous on the subject. They prove that the measure mu beta n that I defined before is a measure on vorticity fields of distributional type. This measure converges to a delta Dirac in a special configuration rho r. Rho is in principle, from this convergence, is an element of this space. In fact, it's smooth, is a time invariant solution of Euler equation, and more up to a little correction that I don't want to write is of this form, is a rescaled, like a mollifier, let's say, rescaled of a certain shape. The shape in the following is only moderately important. Probably I should be able to use it more. One should be able to use it more. But it's very important that it is rescaled of this shape, and the value of this parameter r of rescaling is related to beta. So when beta negative is large, this corresponds to small r. Small r means configuration very concentrated, and so small negative temperature, high aggregation. This is a rigorous result. This is a picture of this profile, just to have a mental image of this profile, which in some sense is universal. Is a profile of vorticity. For instance, there are experiments in which these profiles appear positive and negative, or vice versa, I don't remember, one positive and one negative from an initial state of disordered positive and negative small vortices. However, this kind of configuration are not the inverse cascade turbulence, because this happens in two regimes, essentially. One is the decaying turbulence, so when we don't inject new energy, or another in which the energy is too strong. It could be, but usually the decaying turbulence, this one. And so it's not what I want to describe, but it's important to have in mind this picture that small vortices could aggregate in larger clusters. And now other informations on these measures. There is sorry, I wanted to press the pointer, I made a mistake. So other information on the other extreme, namely I mentioned measures on point vortices. Otherwise, there are measures on distributional fields that can be obtained by point vortices. So originally they were introduced without, but nowadays it's clear how to obtain from point vortices. And so I do that. Assume that we take these weights of the point vortices that scale like central limit theorem instead of the scaling 1 over n of the previous theorem Alain-Zager, let's say. And assume that we take positive and negative signs with equal probability. Then this combination, this vorticity field concentrated in points, converges weakly to white noise. And the white noise is an invariant measure of Euler. White noise formally is written in this form with the quadratic del2 norm, and this del2 norm for the vorticity field is the entropy. So one particular case of the formal writing Gibbs measure that I wrote at the beginning is this case with just the entropy, is called the entropy measure, and is invariant for Euler. Is invariant in the sense the measure itself was introduced around this period, perhaps by Albeverio and other people. In the 90s, Albeverio and Cruzeiro constructed the proved existence of a stationary solution of Euler, so it's a stochastic process which solves a deterministic Euler, and this stochastic process has marginal given by this white noise. And recently I did another proof of construction using point vortices, the limit of point vortices that I mentioned at the previous slide. So the same measure can be the same measure in the sense it is not unique, so we don't know if it is the same measure constructed by Albeverio, but a measure with the same properties, stationary, sorry, a solution of Euler stationary with marginal given by white noise can be constructed either using Fourier components, Galerkin, or using a limit of point vortices. The velocity, this is a measure on vorticity. If we take the velocity associated to this vorticity, one derivative back, from white noise, one derivative back, we are in the area of Gaussian free field. This is vector valued, in this case the velocity is vector valued, so it's a solenoidal analog of the Gaussian free field. And it has some property like conformal invariance. There are works on the possibility that turbulence as features of conformal invariance. So this kind of Gaussian measure, even if clearly, as I will argue also later, is not correct for the turbulence, nevertheless has some feature that maybe is interesting. For instance, this is stupid, I know, but this is just a very fast numerical simulation of what you see at fixed time, frozen time, using 2000 vortices in the scaling I showed, and this is taken in the literature. It looks almost the same. So there is a similarity in the complexity of the field they build, but this is stupid, I know. The spectrum, unfortunately, is completely wrong. And the aggregation, the degree of aggregation is very weak, namely, sorry, no, it's not here, so it's better I mentioned just here. The Gaussian free field has a certain degree of aggregation, but logarithmic, like from the Gaussianity, is the so-called theory of thick points of the Gaussian free field. And we more or less, we have almost a complete proof that the same is true for this solenoidal, but is not the aggregation that is seen in turbulence. So it's just another thing. There are variants. Probably I could skip something here, too many technicalities. Just to mention, there are variants in which not only entropy but also energy. Sorry for the notation that are very confusing, because epsilon can be also energy, so it's difficult to distinguish. So this is entropy, this is energy, and the energy, unfortunately, is infinite. But there is a renormalized energy, alla Vic, that is finite, and one can use the renormalized. In fact, this renormalized is exactly the limit of the interaction energy between point vortices. Point vortices have infinite self-energy, but good interaction energy. If you take the limit of the interaction energy, you get this renormalized energy. And one can define these Gaussian measures well, and also some microcanonical analog projecting on layers of this object. And so there is a large family of measures for Euler equation that are explicit, invariant. There are links. For instance, here I mentioned that the Gibbs measure, which contains both entropy and energy, is with just entropy, I already mentioned, that is obtained as limit of point vortices. But one can do better. One can take point vortices with the coupling due to the interaction energy, rescale, and get this measure. And here there is a list of contributions. And one can do the same at the level of microcanonical measure, to do a microcanonical on the point vortices, rescale, and get to the limit. So we have this family of measures. So the question is, there is one more important thing. Francesco Grotto, that is here, is analyzing a similar object for the model with input and output. Roughly speaking, at the level of point vortices, the input are delta with a Poisson point process appear new vortices with this kind of intensity, and they are dissipated by this. The dissipation just acts on the intensity of point vortices in this way, and it's possible to construct invariant measure and investigate the limit. Which converge again to white noise. So the limit measure in itself is again the white noise before. If you want, this is a confirmation that some of the measures written before can be obtained also for this more realistic model. So this is the first important. The other point is that this mechanism of introducing vortices with Poisson clock and dissipate is at the core of the inverse turbulence. So even if this model perhaps at the end doesn't capture the spectrum and so on, it is important to to have the details written down for this kind of mechanism of input and output of this level. Let me go back to the cascade, and now I'm going to start a part of the talk which is not based on rigorous works. Unfortunately, I noticed that I have too many slides, and so I will jump something. What one would like to do is clear. One would like to modify these measures or the scheme in order to capture cascade in a strong sense and this spectrum. What now I believe is that using just the point vortices is more or less impossible, unless the point vortices are used in a very special way that I'm trying to describe now. We have to replace essentially the basic idea that is, sorry, sometimes the basic idea is to replace the point vortices with finite size vortex structure. This is absolutely clear that in reality they are not point vortices but finite size structures. And the point is that this is essential for understanding the inverse cascade. Finite size structure, there are more or less blobs and filaments. To simplify, filaments, I don't know now how to use them, even if I like very much, but so I will use blobs. And I will try to use the blobs of von Zager, replace the point vortices with the blobs of von Zager that I described before. But there is another ingredient, that instead of the blobs of von Zager as a continuum function, I will think about point vortex approximation of them. So the statistical mechanics of point vortices which approximate this blob will be always in every slide extremely, sometimes is absolutely essential not to use this as a continuum object, but to think that this is the idealization of a huge number of point vortices.
Question. Yes, you introduced viscosity, that was a length scale for the vortices. Is that what you're mimicking with this structure?
Viscosity, I neglected the viscosity. You say if I want to introduce...
That introduces the length scale for the vortices.
I don't know. I think that viscosity is infinitesimal. There is one place where you will see it plays a role. Otherwise, if I'm not able to incorporate viscosity in this scheme. The point vortices immediately. I understand what you mean. That, the size of this is not related to the size of viscosity. So if there is a length scale of viscosity, is not the one which produces this object. It's just the one that that produces some averaging when there are a lot of vortices, produces some averaging and smooth out the configuration. This is the only effect of viscosity that is relevant in the discussion. And so, in the spirit of the model of Francesco Grotto that I mentioned before, I assume that at some small scale, I introduce these blobs, positive, negative. At the end of the story, for the discussion, it's sufficient to have a positive. But the blobs themselves are made of very many point vortices. I will draw only few, but think to very many in a statistical mechanic sense. And there are two phases. The second one is the important one, but let me start with the first phase, regime. First regime is the one in which we still inject a few of these structures. These structures are relatively isolated, like here. And when the structures, when these vortex patches are relatively isolated, they can be analyzed rigorously. Here I didn't write explicitly a theorem, but there are several theorems also in my paper that I mentioned above, of that if we have vortex patches at time zero which approximate the delta Dirac, then the same is true at later time. But of course the radius of these patches must be small compared to the distances between the points. So there is at the beginning something that mathematically is manageable. The problem is that we introduce more and more of these vortex patches, and when the number is sufficiently high, there are pairs like this one. And now we see what happens to the pairs like this one. When they are distant, this is a numerical simulation with 200 and 200 point vortices. When they are distant, they behave like the center of mass, like two point vortices with the same sign, which turn around, the one around the other. There is an internal deformation, a stretching due to the rotation produces a stretching of the other. But if the stretching is not strong enough, you have to think that the red structure is rotating not only around the blue one, but in itself is rotating. So this stretching is completely destroyed after a few seconds because the structure rotates and reconstructs the round blob and repeats periodically this until by a fluctuation the stretching is so long that the two structures get in contact, and when they get in contact they start to merge. If the completely different is when we start nearby. There are several remarks, but I have to speed up. If they are close each other, they start to merge immediately, and more or less in one turnover time, they have built a structure of larger size. If this is another simulation with a little bit closer structures, and so the philosophy extracted by this is that two structures of Onsager type in one turnover time give rise to structures which are approximatively of Onsager type. Approximatively for several reasons, including these wings. The importance of these wings perhaps there is, but it's difficult to quantify. So I drop some slides because otherwise I am too slow. But here there is some philosophical remark that I would say. Now I go to some other mathematical detail, but in some sense there is some form of local equilibrium in this non-equilibrium problem, but is sometimes quantized. So it's not that in every portion of space we have local equilibrium. This is quantized in some complicated way, multi-scale way. And the other feature that is absolutely essential is that the convergence to equilibrium requires a macroscopic time. So that is not true, there is not separation of scales that in arbitrary short time we get arbitrarily close to equilibrium, unfortunately. So everything is made complicated by this macroscopic time of convergence to equilibrium and the fact that there is a multi-scale structure. But the idea that there could be equilibrium behind, the Onsager equilibrium, this is fascinating. Let me write some formula to understand. This object is the interaction energy between two Onsager structures, like picture here, at a distance d, one from the other. So this is the kinetic energy of two structures of Onsager type, and let me call G of d. If this is one point. Now assume that we have two structures of that kind at scale r. Before there was not scale r in the picture above. With the scale r, you apply a little scale argument, and you compute that the global energy of the two structures together is made by 2 times the contribution of each one plus 2 times the contribution of interaction, this G of interaction written before. And there is the term log 1 over r. R is the radius of this. And the intuition from the numerics is that this structure merge in one new Onsager structure with a new intensity, a new radius, which has a final energy, again computed by the same kind of formula, which is of this kind. In a second, I will explain that the new intensity is twice the old intensity, so extremely easy the rule for the change of intensity, and extremely mysterious the rule for the passage from R to R tilde. R to R tilde, namely the radius of the two structures before merging with respect to the radius of the structure after merging. But before doing that, let me recall a theorem from Lyon's Marchioro Pulvirenti papers. If you take the microcanonical measure on a finite number of point vortices, so the flat measure on an energy, instead of the surface I take this, energy greater than threshold, is the same. So if I take the microcanonical measure, with respect to the microcanonical measure, the empirical measure of these point vortices converges to one of these Onsager structure with a value of beta, of the negative temperature, related to H, namely to the value of the interaction energy between the particles. Let us try to see what this theorem tells us. We have two Onsager blobs. We consider the Onsager blobs like point vortices. These are the Onsager blobs in the continuum. This configuration, or this one, have more or less a certain energy computed in the previous slide. And so this configuration of n vortices x and n vortices y live on the energy surface, so to speak. And due to this theorem, when it lives on the energy surface, in the limit, when n goes to infinity, it is described by this kind of universal shape with respect to a certain beta parameter. So the energy of the two blobs approximated by point vortices was given by a formula found before. The two blobs together as a collection of point vortices is like a new configuration of vorticity, in which if I want to have the same number 2n here and 2n here, I have to double gamma. So this is the simple rule why gamma is doubled in this process of merging. And we find that statistically these points are described by this Onsager configuration, which is the radius. The radius is related through beta to the original h, or more simply is given by the identity found 2 slides ago between the energy at the end and the energy at the beginning. I completely understand that it's impossible to enter such a formula during a talk. What I want to say, here gamma can be simplified. What I want to say from this formula is that the value of r tilde with respect to r, the original r, depends on the relative distance of the 2 points. When I started this research some time ago, I had the illusion that from this identity the Kolmogorov spectrum could emerge already without additional information. Still now I'm not sure that this is wrong. If one can discover that r tilde over r is equal to 2 to the power 3/4, then it is possible to deduce Kolmogorov spectrum. Unfortunately, the ratio between these two is related to the distance of the two clusters before merging, and the distance is not uniquely prescribed. You can imagine that I tried numerical. I took two clusters just in contact to try. I did the simulation. I computed the ratio at the end, and it was 1.68, which is the same number. So inside the merging of two structures, there is presumably already the answer of Kolmogorov spectrum. The problem is that from this relation there is an ambiguity in the distance, because there is not only one distance that produces merging. It's possible, just to, I don't have slide on this remark, but I think it's quite important. It's possible that this relation should be corrected, because as we have seen in the numerics, there are wings at the end. So at the end there is a sort of Onsager structure plus wings. The wings are bigger if the distance is larger. It's possible that there is a compensation between the energy lost in the wings and the ambiguity of this radius. So if it is possible to reconcile everything, maybe one discover this law directly just from the merging of two Onsager structures. So Kolmogorov spectrum would be just the result of one step of merging of structures. I'm not sure about that. It's still part of the dream. I'm going to complete my time in 5 minutes. The other part of slides is to remove this problem. Namely, I cannot deduce that this ratio is the right one from here. By the way, why I say that from here we deduce Kolmogorov spectrum? Because the gamma moves, the old gamma goes into 2 gamma, r goes into r times 2 to the power 3 over 4, and so gamma to power 3 over r to the power 4 is constant in time, doesn't change in time after merging. If you put this equal to a constant, you deduce that gamma is a constant times r to the power 4 over 3, and the velocity is, by simple argument about the Biot-Savart kernel, the velocity is gamma over r, so is c r to the 1 over 3. What is missing from this argument is the role of epsilon, the injection energy, but the scaling immediately comes out. Okay, the rest of the slide is impossible in 5 minutes. I want only to explain the principle. 10 minutes perhaps. I try to explain. Here there is something that is nice, because I already mentioned that entropy is certainly lost in this process. If I use Onsager blobs as continuum, I don't know how to prove that there is a change in entropy. But since I analyzed this picture of merging through the theorem of Cagliotti, Marchiori, etc., which is a theorem on point vortices, I deduced the law that gamma doubles, and if I compute the entropy before merging, which is the entropy before merging is 2 times the entropy of each initial configuration. The entropy at the end is 2 gamma of the final configuration square. You do the computation, and you find that the initial radius and the final radius should differ by square root 2. Square root 2 is certainly wrong. The correct value is around this. So there is certainly a very precise entropy dissipation, anomalous entropy dissipation, because formally entropy is invariant, anomalous entropy dissipation inside this process. So it's a relatively deep process that one should obviously understand better with respect to what I'm telling. To collect the local picture of this structure that merge into a global picture, the only way I can do now is to put assumptions, to make ansatz. The simplest is to assume, okay, there is an injection scale level in which I inject these small vortices. I have to assume that when the vortices reach a certain distance, they start to merge. And the simplest is to assume that this goes in levels, namely that vortices of the same radius merge into new vortices of a new radius. Vortices of the same new radius merge into larger, and so on. This is certainly wrong, in the sense that it is absolutely sure that if you have a big vortex and a small vortex together, they also mix up. But this probably is a second order correction, because the time of mixing is dictated by the largest vortices. That the largest vortex has to make more or less 1 or 2 turnovers, and so it takes a lot of time for a small cluster to merge with a larger one. the time of merging between two clusters of the same size is much faster. So probably statistically it is really dominated by the merging of clusters of more or less of the same size with respect to all the different other possibilities that one can image. And so one can construct, it is clearly a huge approximation, layers of radius, different levels, image the vorticity as a multi-scale structure. The assumption one is the one that I said, that I use only merging of structure of the same size. Here there are something too technical that probably I cannot explain. Essentially, please don't read. The essence of this is that the typical time of merging is of the order of one turnover. I have to assume that what I observe in numerics, namely that in one turnover or two turnovers there is merging, is correct. If I assume this at scale 1, just rescaling using Euler equation, rescaling, I have the following rule. Here is a picture of, in one turnover, more or less, we have reached the same result from two different distances. Rescaling this assumption from scale 1 to any other, sorry, drop this, we arrive to this rule, that the time of merging of structures at level A is the ratio between the radius of the structure and the intensity. It's just a very easy computation showed in the previous slide. So until now I discretize the levels for simplicity. I assume that the time of merging is given this way. This is not important as an assumption, but is probably satisfied. But alpha is not determined. If I say that alpha is 2 at power 3/4, it's done. I don't need all these arguments. And then I have used stationarity. Right. Just in few words, without showing the details, I have to use the stationarity of this process in time, so I have to assume that the process from few vortices at time to grow up and create a stationary regime. In these different layers, the energy flux is the same, like in a linear queuing network, equating this energy flux with other quantities which are in some sense computable from the Onsager structure, like which is the energy of each structure and which is the number of structures that merge. It requires some work to do that, but for instance, let me show one possible computation. The energy of a single structure is of the order gamma square with a logarithmic correction. The number of structures that merge in unit of time, the number of structures that merge in a unit of time is related to the time of merging that I mentioned above. I'm sorry that my time is over, but you can believe that if I put everything together, I find that the energy flux at each level is given to the ratio written there. So the constant C written there, the blackboard, is precisely up to another constant, which is around this, up to another constant, is it depends linearly on the energy flux, and so at the end one gets exactly the law that the velocity is equal to, statistically speaking, to the radius 1/3, where this constant is epsilon to the power 1/3 also. And so in a sense, summarizing, sorry, I jump this computation that explain what I said. I go to the open question, little summary. In summary, I used the two ingredients. One ingredient is this understanding that two Onsager structure merge with special properties. And the other ingredient is a sort of a queuing network structure at equilibrium, which probably is necessary or probably not if one can understand even better the merging of two structures. Open questions, very many. extremely difficult is to guess an explicit probability measure on vortex configuration that reflects this idea of blobs, because we can only do points or distributional fields, nothing else. Another extremely difficult but more general than fluid dynamics is to understand non-equilibrium systems. In particular, here there is a sort of non-equilibrium system that has a quantized local equilibrium and macroscopic relaxation time. Maybe one can build a simplified model in which one can investigate this pair of properties. And partial steps just to do something easier is to disprove, of course, not to try to find the confirmation, but to disprove what I said. Until now, every objection that I found at the end of the story, I thought this is irrelevant. So, but there could be serious objections. Prove fragments of the scheme, for instance, the quantification of convergence to Onsager equilibrium. So the fact that the 1 or 2 turnover times are sufficient to get close, quantification, rigorous quantification is completely open. And the onset of the cascade, the phase when there are still few vortices, probably is amenable of mathematical description. So this is another fragment that could be done. Or investigate a simplified model. Here in the audience, Luigi Amedeo Bianchi and Francesco Morandin, they have recently found on a dyadic model on tree for the three-dimensional cascade, they have found the so-called intermittent structure function. And in these days, they computed over the same model the inverse cascade, and there is no intermittency. So what I want to say is that probably there could be simplified models where one can formalize some of this thinking. Thank you, and sorry for that.
Thank you very much. Are there any questions?
When one looks at vorticity in inverse cascade, and one sees that sort of typical vortices are of the order of this injection scale, whether build or rarely build bigger ones.
Right.
So how this is sort of compatible with your picture, which sort of says that the main mechanism would be the coalescence of vortices for transfer of energy to larger scales? In a sense, the two clusters that will merge in one is a very particular out of equilibrium configuration. The most standard would be to take a flat disordered set of vortices and observe that they group. The two clusters is another initial configuration, one of those which are not statistically observed at equilibrium, and they will rearrange to build the structure. This is the analogy. The analogy with the phenomenon of grouping of vortices is that the two structures is like a very special configuration, different from the typical one that we observe. And this is what my intuition.
Any other questions? Yes?
Have you found any analogies with your work with active matter systems? Because the thing you're describing there seems to, for me, intersect a little with that.
Active agents?
Active matter, yeah. You're pumping in energy, and you have hyperbolic transport, in this case vorticity.
No, this I don't know. I cannot answer. Yes, understand. No, very beautiful question. Sorry, I cannot answer.
Yeah, when you consider the two vortexes, no, and then you take into account the interaction energy. But did you try to consider the fact that if there are other vortexes around, they could screen and diminish this effect?
This is the huge difficulty, that all this, if it is true, this idea of convergence to an Onsager equilibrium, this happens in the middle of other objects, and so it takes a macroscopic time, and in this macroscopic time around there are other structures that perform this. So it's not that this will converge to the equilibrium. just will approach a little bit the Newton-Zager configuration of equilibrium, and immediately this object is subject to another transformation. So this is a sequence of metastable states, but they don't have time to stabilize in the usual sense of equilibrium, of local equilibrium statistical mechanics, because there is no separation of scales. So what you say is perfectly correct, as in in principle an objection.
Yeah, no, I was saying maybe something different and in favor, actually.
In favor.
That is, if you have too large vortex, then you have small vortex around.
Right.
And I mean, with the charges, they usually act in screening the two big charges. So the interaction energy maybe could be lower than what you think, because of the presence of smaller vortex, which they go in equilibrium faster, so they should be in equilibrium between the two large big vortex.
Very interesting, thank you.
Yeah.
Thank you again for that.
Thank you.